Hello everyone, I'm Hao-Lun Yeh from Colorado State University, and it's my pleasure to talk about our research on unbiased fully nonlinear data assimilation and the stochastic particle flow filter. And this research is funded by the National Science Foundation of the United States. So in the beginning, I will give some background information and the motivation for this study. We all know that the nonlinearity in numerical models or in that data assimilation have become really strong, so they cannot be ignored with increasing model resolution and more complex operation operator. So nowadays there are some possible solutions, but also have some challenging there. Some communities use the ensemble common filter or hybrids with their variation methods. And this method really work really well in some linear scenario, but for the nonlinear dynamic, they might use several settings such as localization and inflation to mitigate this problem. Others are the fully nonlinear data assimilation methods, such as the Markov chain Monte Carlo methods. It can directly draw the sample from the posterior and give accurate results, but due to its burning period, it is very efficient in high dimensional systems. The third one is the transport maps, and which has the benefit that machine learning can learn from such map, but it also needs an efficient localization strategy for the high dimensional problems. And recently, the particle filter have become one of particular methods to solve the fully nonlinear problem, but it suffers from the long existing weighted degenesis problem. And this problem can be partly solved by localization, but there's one method that can efficiently sample the posterior and avoid the weight degeneracy. That is a particle flow filter, which is a sequential Monte Carlo filter based on the Stein variational gradient descent. And a particle flow filter is similar to one of the popular existing method, which is an ensemble of 40 bar. Here we make a clear comparison and express it in a steep descent form, which is the updating method as the particle flow filter use. And although in practice, ensemble 40 bar uses a conjugate gradient to update each ensemble. For the ensemble 40 bar, it needs to perturb the observation first, and then minimize the cost function used for independently for each ensemble member, and make them move toward to the log of the posterior. So the ensemble 45 is a weak nonlinear data submission method with the independent update, and it needs a produce observation. For the particle flow filter, is a fully nonlinear DA, and without any constraint in the prior distribution and the linearity assumption. And different from the ensemble 40 bar, the particle in the particle flow filter can communicate during the minimization through the kernel. Like this formula is shown here, and you don't need observation. However, the particle flow filter is known to have a bias ensemble spread in high dimensional system, and with a small number of particles. And recent research proposed a particle flow filter with the new matrix value kernel that can avoid the particle collapse in high dimensional system, but is still biased. And another recent research provide the particle flow filter with the additional Gaussian noise term that can lead to the truly correct stationary posterior distribution, which means it has no bias in the algorithm. And we come with the additional stochastic term here. So the goal of this study is to propose an improved and efficient variant of particle flow filter algorithm shown like here. There's a stochastic version of particle flow filter that can solve the high dimensional nonlinear problem with unbiased sampling. The key idea of the method is try to push forward the particles from the prior to the target district density with equal weight in the so-called deterministic flow and include the Gaussian noise additionally. The first term is called the attracting term. It tends to make all the particles approach to the mode of the posterior. And the second term is the called a repelling term, which tends to separate the particles from each other and prevent particles from collapsing. And the final term is the stochastic part, including diffusion process. Here we give some example. figure shows the posterior and the prior and posterior distribution in the first assimilation cycle. The blue dot are the prior density samples, where the red dot represent the dots after the application of the method. And the gray line shows the trajectory of the particles, and the vertical axis is the pseudo time step. And we can see that the particles collapse to the mode of the posterior in a high dimensional system. And a new version of particle flow filter used a matrix value kernel where the particles can better communicate with each other. We can see that the particles won't collapse, but the spread is somehow the bias high. And our new stochastic version brings the noise into the original one with the scatter kernel. And the results show that the ensembles won't collapse by using a scatter kernel and with reasonable size of spread. Here shows an animation to illustrate the sampling process of the determinist and the stochastic update process. This is adapted from the Lavier et al. In 2002. We can see that there's an additional random process in each iteration for the stochastic method. This random process actually makes for a more efficient exploration, and it can be expected that it will result in much more lower estimation errors. To evaluate the feasibility of the stochastic version, we conducted several experiments based on the 1,000-dimensional Lorentz 96 model. We used 20 ensemble members, and there are 25% of system is observed. And we used two different operators to investigate the general behavior of the particle flow filter. We have three experiments as we see in the last slide. The first one is the original version, which is the one used the scatter kernel. And this has been known to have a particle collapsing. And the second one is the newer version, but has some bias, which use the matrix value kernel. And the third one is the stochastic one. In theory, we need to use the scatter kernel instead of a matrix kernel to get the unbiased sample. And here show the time series of the trajectory. And when using a simple linear observation operator, we see that the particle flow filter with the scatter kernel has a filter divergence shown like here. And while the other two methods have improvement of the evolution compared to the NODA and comparable performance with each other. And this result suggests that the stochastic version can actually indeed prevent the particles from the wave degenesis with additional Gaussian noises, even use as original scatter kernel. When it comes to the spread, we should mention the kernel width, since the kernel width can directly control impact the spread of the particles. A wider kernel width can lead to the larger spread of the posterior, and narrow one can act on the opposite way. So a too small kernel width may lead to a small spread and cause the filter divergence. Here we discuss the sensitivity of the method to a kernel width in terms of the Rubin square error. So the horizontal is the mode, is a model time step, and the vertical value is the Rubin square error. It shows that the particle flow filter with the scatter kernel original one, no matter what kernel width is, the system diverges all away from the true state. On the other hand, the stochastic version has a stable performance with the kernel width of thousands. This suggests that a particle flow filter with scatter kernel was only with the additional repelling forces with the noise term, but only when the kernel widths are reasonable. With this kernel width, the results show the stochastic version can slightly improve the Rubin square error posterior, like the top right figure shown here. And when we then compare with the ratio between the Rubin square error and the spread of the prior in bottom right figure, the blue line is particle flow filter, which the original one is the stochastic version. The solid line is the Rubin square error of the prior. and the dashed line are the corresponding ensemble spread. And the value of 1 can be seen as the equal to 1 can be seen as having a good and reasonable spread. The results show the stochastic version has the ratio more approximate to 1 compared to the deterministic one. So we can conclude that the stochastic version with the reasonable kernel width, which is 1000 here, has a comparable performance, even better, comparable performance with the deterministic one, but with the less bias in the spread. And then we evaluate the performance of the newer method when the observation operator is nonlinear. And here we show the example of the square operator. If we take a look at the prior and posterior distribution with the trajectory in the first assimilation time, it shows that the stochastic dispersion converges to the posterior faster than with and the deterministic one with less iteration number. You can see like here. And for the time series of the evolution, the red cross is represent the true state value, and the blue cross represent the opposite side of the true value. We found that both deterministic version and the stochastic version can capture the biomodel structure of the particles. But for the unobserved variables, the stochastic version has the better ability to capture the biomodel distribution with the fixed iteration number due to the more efficient sampling shown like here. However, we notice that by examining the root square error, the stochastic version with the kernel width of 1000 doesn't have a better performance compared to the deterministic one. So we do another sensitivity test for the kernel width again, and the results show that the experiments with the smaller kernel width has a better performance in terms of the root mean square, which is shown equal to 20 or 100. This suggests that the square error operator kernel width size of dimension is not optimal one. We presume it is because the biomodel structure of the particles has better performance with the less spread. If within the time series of evolution, only about half, like here, half particles around the truth when it has a biomodel structure, which means it's only need half of a spread to capture the truth. Therefore, we proposed a so-called adaptive kernel width to find the appropriate one kernel width automatically. We only need to do is presume the initial kernel value as the size of a system, which is 1000, and then we adjust the kernel width with a factor which is square of the ratio of the absolute value of prior spread and prior spread value itself, and we adjust it in each assimilation cycle. The results show that the kernel width converges to the value around 500 finally. If we do the experiment using an adaptive kernel width, we get a slightly better performance compared to a deterministic one. So for the nonlinear operator, we suggest the user to use a adaptive kernel width so that we do not need to tune the kernel width manually. To justify the results, we conduct experiments with a larger iteration number to make sure the method converge sufficiently. We can see that the experiment with the small kernel width diverge in a later cycle, shown the green orange line here. While the one with the 500 has the stable and the best performance, which is correspond to the value provided from a adaptive kernel width, which is the 500 shown in the last slide. So the smaller kernel width seems to give a better performance shown in the previously, but it actually not stable. Using a adaptive one can give a good and stable result. By comparing the ratio of the spread of it is also demonstrating the stochastic version has a bias in spread, has less bias in spread, and also it has comparable root mean square error to the determinist one. So generally, for a nonlinear operator, adaptive kernel will give a good result and stable performance, produce a reasonable spread in the meantime. So from now, all right. For now, we show these promising the result of stochastic particle filter for its efficiency and less bias. When I evaluated the performance using larger ensemble members, as mentioned before, the stochastic version has more efficient sampling, so use a larger number of ensemble can address the advantage of the efficiency of the stochastic version. So from time series observation, especially in the unobserved variable, it shows that the stochastic version have the trajectory of true state really well, with less but reasonable spread, and the size of spread is as large as the one in the experiment with small number of ensemble members. And we can see that the stochastic version have a comparable performance in the posterior, but have improved short-term forecast and less bias. For our future work, the first thing is to optimize the setting in simple ocean model experience to improve the stochastic version. And then we will evaluate the performance of the stochastic version in the real-world numerical models. And then finally, we will extend our stochastic version to the smoother version. In this way, it has the computational similarity with the ensemble of the 40 bar. So here is my comes my summary, and I stop here. Thank you for my listening my talk.
Thank you, Hao-Lun, for an interesting talk on the stochastic particle flow filter and extensive experiments showing the impact to different settings of the kernel. We have a couple of, actually 2 questions in the YOPAT, and I do invite all the attendees to add more for the speaker, but I'll start with the first one coming from Javier. He's asking, I did not get why the stochastic particle flow filter works with a scalar kernel, but not with a matrix valued kernel.
Okay, so the first question is why we don't combine the stochastic version with the matrix value kernel. That is because from this research, it demonstrates the determinist one actually is the spatial form of the MCMC method. It also combine this Stein the Stein gradient descent dynamic into the MCMC method. It found it is a spatial term. In the derivation, it should use this scalar kernel term so that it can derive the actually stationary posterior results that has the no bias. So that's why we use the scalar kernel here.
Okay, this is great. And second question is from Lars. He's wondering, is getting a good result from the stochastic particle flow filter a question of finding a good kernel, or is it more to do with good randomness? Is there analytical insight about what is right?
So, let me give you some. So in the previous research in 2019, when the sequential version of particle flow filter comes out, the author suggests the proper kernel width is the 1000 is the dimension size of the dimensional. In the formula can actually balance the spread, but if you discuss with the dynamic, so the kernel width is acting like the measurement of their average their distance between the particles. So for the scalar one is the average distance, and metric value kernel is the measure independent. So the reason why using 1000 is there's It's not shown here, from here, but it's for the summation of the distance, and we should divide it the size of dimensions so that it can get the average value. So that's why we use the size of dimension, but we cannot express it explicitly here.
Yeah. Well, feel free to also elaborate on the questions in the YOPAT and to, if you would like to answer in more detail there. But with that, thank you so much again for your great talk. And we look forward for more developments on the particle flow filter landscape.